Good evening, everyone. First of all, let me thank you all for coming here today. So, our universe is so vast, and there's still so much we don't know about our planet. So, one recent discovery was the Schumann resonance, which is considered by many to be the heartbeat of our planet, which was only first mathematically predicted in 1952 by physicist Winfried Otto Schumann. I'm Maurya, a second year undergrad from Department of Electrical Engineering, who's here to build a basic understanding about Schumann resonance and the history behind it. And welcome to the seminar. This presentation is structured as follows. First, we'll talk about what is Schumann resonance and how is this happening. Next, we'll of course talk about the man who Schumann resonance is named after, Winfried Otto Schumann. As he's a very important person in the seminar, I thought of going about a short biographical summary. In section 3, we'll talk about the people who contributed in the historical development of the problem of propagation of electromagnetic waves in a cavity. And in section 4, we'll talk about Schumann's work regarding the long wavelength oscillations in the Earth-ionosphere cavity. And at last, the aftermath, the further developments about the same. So, to understand what the Schumann resonances are and how it is produced requires a little bit awareness about the macro geophysics. Above the ionosphere is the magnetosphere with a strong magnetic field, as you can see here in this picture. It helps us to protect our Earth from strong bursts of highly charged particles from the outer space due to the collision of stars. These charged particles interact with the field lines, which causes the aurora borealis, also known as northern lights, and aurora australis, also known as southern lights, which you can see in the background. They also drives electric currents in the ionosphere, which influences weather in our planet. So basically, Earth acts like a giant circuit, and the atmosphere is actually a weak conductor, which implies no source of electric charge. So the energy would dissipate, right? But it doesn't. That's because the solar radiation from the outer space makes the ionosphere conductor and gives the ability to trap the electromagnetic waves. So these particles, charged particles, when accumulated near the surface of the Earth, can form thunderstorms. About 2000 thunderstorms will produce around 50 flashes every second around the Earth. This accounts for much of the measured flow in this cavity. The photons radiated from the thunderbolts interact with the ionosphere and refract back to the Earth or towards the ionosphere again. So, what do all these mean? There is a great deal of electrical activity is present between the Earth and the ionosphere. These refracted waves are trapped between the Earth and the inner edge of the ionosphere, which is approximately 60 miles, which will act as a waveguide for these waves. Some are in the form of standing waves of electricity, and these are called the Schumann resonances. As you can see in this video, the waves are trapped in the Earth ionosphere cavity and they keep on traveling with them acting as a waveguide. In our case of Earth, the sweet spot for resonance is the wave to be as long or more as the circumference of the Earth. Traveling at the speed of light with its wavelength equals the circumference of the Earth, which is around 40,000 kilometers, is the foundational Schumann resonance. This is an extremely low frequency wave that can be as low as 8 Hz, 7.83 to be exact, which is some 100,000 times lower than the lowest frequency radio waves we use to communications. Along with weaker harmonics around 14.3, 20.8, 27.3 and so on, meaning our atmosphere is continuously resonating with these frequencies. The frequency of all modes can vary slightly owing to solar-induced perturbations to the ionosphere. These waves acting in resonance with each other will pump up the original signal. So, with the lightning discharging approximately 50 to 100 times per second around the world, the Schumann resonance is constantly being fed with new photons of energy and therefore is a stable frequency of light. So depending on the intensity, frequency and distribution of lightning strikes across the world, the Schumann resonance can vary in amplitude but is always present in the electromagnetic spectrum. As the frequency increases, which are spaced at approximately 6.5 Hz intervals, the intensity of the mode decreases. So, the lowest frequency mode will have the highest intensity. Now, that we understood what Schumann resonances are, we'll talk a little bit about the man after whom the term Schumann resonances are named after, Winfried Otto Schumann, who was born on 20th May 1888 in Tübingen, Germany, whose father is also a physical chemist, Ernst Otto Schumann. He studied electrical engineering at the now named University of Karlsruhe from 1905 to 1909, and he worked as assistant to Engelbert Arnold and prepared his doctoral thesis on the torques of the damper winding of a multi-phase synchronous machine at small pendulum oscillations in parallel operation under Arnold's guidance to earn his doctorate in 1912. After then, he started to work in the industry as head of the high voltage laboratory for the company Braun, Bovary and C at Switzerland until 1914. During the First World War, he served as a radio operator. Also, this picture in the slide is took when he was on a United States Marine troop carrier during 1947. So, in beginning, in 1990, he worked as research assistant of the Robert Bosch Stiftung in the University of Stuttgart. He also qualified for university teaching in 1920 with a thesis on electrical breakdowns of gases. In the same year, he was appointed as associate professor of technical physics at the University in Jena, Germany. In 1924, he was appointed full professor for theoretical electrical engineering at the Electrophysical Laboratory at the Technical University of München, Germany. From 1947 to 1948, Schumann worked at Wright-Patterson Air Force Base for the United States Air Force. The picture in the previous slide was took during this time. In 1961, he was given the status of Professor Emeritus, but he remained active in research until his death on 24th September 1974, and this picture was took in 1974, the year of his death. So, 4 distinct periods can be distinguished in the scientific career of Winfried Otto Schumann. Until 1924, he was mainly dedicated to topics in high voltage engineering. From 1924 until 1951, he worked on discharge phenomena in highly ionized gases, plasmas, and also on wave propagation. In the third period, which is important to us, from 1952 to about 1957, he was devoted to investigations of the propagation of ELF waves, that is, extremely low frequency waves, in the cavity between the Earth's surface and the lower ionosphere. After his retirement on 1958, he worked mainly on problems of the motion of electrical charges under the influences of low frequency electromagnetic fields. His scientific work was honored when he was named a member of the Bavarian Academy of Sciences and Humanities in 1945 and by the granting of an honorary doctorate by the Technical University of Darmstadt in 1957. In this section, we'll talk about the investigations of the problem of wave propagation in the space between concentric spheres in the pre-Schumann era, that is, years before 1952. We have to understand that the simple model can only serve as a crude approximation to reality, as there are a lot of non-idealities. First, both Earth and ionosphere are not perfect conductors. Conductivity of air is not constant, but varying along the distance from the Earth, and effects of Earth's magnetic field is not taken into account. So, due to these non-idealities, it differs in several aspects from the system. So, keeping this in mind, let's proceed. The first mention of electromagnetic oscillations in a cavity between concentric spheres can be found in the book on electricity and magnetism by Joseph J. Thomson, published in 1893. In his book, he mentioned about the oscillations between two concentric spherical conductors. He took a case of the vibration of a spherical shell excited by some cause inside, so there is no radiation of the energy into the space. The electrical waves keep passing backwards and forwards from one part of the surface of the sphere to another, right? He considered electrical oscillations on two concentric spheres of nearly equal radius and calculated the wavelength to be pi times square root 2. This expression for the wavelength of the lowest resonance frequency wave is the same as the one Schumann derived in 1952 for the Earth-ionosphere system. Now we have to appreciate this. He is the one who proposed the first structure for guiding waves back in 1893, and this led people after him to have a wide thinking space. Next person, George F. Fitzgerald. In 1893, Fitzgerald presented a talk during the 63rd meeting of the British Association of the Advancement of Science in Nottingham, United Kingdom. In the talk, he explained that the period of oscillation of a simple sphere of the size of the Earth would be about 1/17th of a second. But there was a hypothesis that the Earth is a conducting body surrounded by a non-conductor. And he concluded that this is against the fact. So he predicted that probably the upper regions of our atmosphere are fairly good conductors. So he used the Geissler tube, which was invented in 1857, to explain this. A Geissler tube is a gas discharge tube used to demonstrate the principles of electric load discharge, which is similar to modern enlightening. In this tube, air is a good conductor, and we know that when part of a gas is transmitting an electrical disturbance, the rest of the gas becomes capable of that as well. Using this, he assumed that during a thunderstorm, the air becomes capable of transmitting small disturbances. If the Earth is surrounded by a conducting shell, its capacity may be regarded as that of two concentric spheres and not a simple sphere, which would produce a corresponding change in the oscillation. If you assume that the height of the region to be 60 miles, we get a period of oscillation of about 0.1 seconds. But later it was found that he made an error in his calculation. But it seems that Fitzgerald was really the first one to consider the so-called Schumann resonance problem. Only an year after Thomson's and Fitzgerald's investigation, Joseph Lamro, then lecturer at St. John's College, Cambridge, calculated the free periods in a uniform spherical condenser in 1894. He assumed that the separation between the spheres is small compared to the inner sphere radius and derived this formula in the slide, which is 2 pi a by c times 1 by square root of n times n plus 1, where n is an integer. And this formula is exactly the same one Schumann derived in 1952 and applied to the analogous Earth-ionosphere cavity. And the next person, Nikola Tesla. Some still spread rumors that the Schumann resonances had been originally suggested by Nikola Tesla, but none of these publications gives any citation to a relevant Tesla publication for the claim. But this persists till date. He proposed three requirements for resonating conditions, as you can see here. First, the Earth's diameter should be an odd multiple of the 1/4 of the wavelength. Second, the oscillation should be employed such that the radiation loss is minimum. And at last, irrespective of the frequency, the wave train should continue for at least 1/5 of a second. Also, we can see that many of Tesla's early experiments have an intriguing similarity with later developments in ELF communications. Tesla proposed that the Earth itself could be sent into a resonant mode at frequencies of the order of 10 Hz. So later in 1977, a person named Waite apparently dug further into Tesla's ideas and found that Tesla was convinced that the Earth itself could be resonated by choosing a frequency that would permit constructive interference. And also, in a Tesla's patent in 1905, he clearly outlines that the idea of the Earth as a resonating circuit when he did not even know of the ionosphere, which was confirmed in 1924, and estimated the lowest resonant frequency as 6 Hz, close to the 6.6 Hz for a perfectly conducting sphere. These contributions made by Tesla were really important for the further research in the field. There are other minor contributions from other people, but I will not go in detail about their work, rather a quick overview of what I understood as they are minor contributions towards our topic. So, McDonald pointed out that in the case of an ideal cavity resonator, there will be an infinite number of resonant frequencies with decreasing amplitude and spacing as the frequency increases. In the real world, the losses in the Earth-ionosphere cavity, the related damping, only allows the first few resonant frequency peaks to be observable above the background noise level. So, he derived a bunch of formulae which I will not put here, but will give the links to these books for you to further read about it. Next up, Rydberg. He considered the propagation of radio waves around a spherical Earth surrounded by a concentric layer with a high distribution of the electron density, which is the so-called episteme layer, and developed a complex set of formulae for a spherical Earth-ionosphere cavity. He did not explicitly calculate the roots of the equations, but did an extensive discussion of the quality factor of the Earth-ionosphere waveguide and its consequences for the Schumann resonances. And a lot of people like Anton Lampa, Gustav, John, Harry, and John also contributed to the problem of wave propagation in Earth-ionosphere cavity. Next up is a section which covers the contributions made by Schumann for the problem of wave propagation in the Earth-ionosphere cavity. So, regarding the same, Schumann published 5 articles in 1951 and 52, with one in October 1951, one in January 1952, two in August 1952, and one in October 1952. He considered a transverse magnetic wave and derived an expression which is shown here without any dependence on phi from the radial vector potential. Here, capital H and small h are Bessel functions. Bessel functions are like canonical solutions to the Bessel differential equation, whose expression can be found from the web. Also, in this paper, he calculated the lowest eigenfrequency and he derived an equation for the wave harmonics, which I will put up in the slide. In his second paper, he deduced an approximation for the attenuation of the lowest eigenfrequencies of the Earth ionosphere cavity and determined the attenuation factor as the quotient of the mean absorbed heat and the average total stored electromagnetic energy. If you want to go through his papers, I'm putting up the links for them at the end of this presentation. You can check this derivation if you want. In his third paper, he derived an approximate formula for the wave propagation in the Earth ionosphere cavity, which is excited by a dipole and lightning discharge. The fourth paper was like an extension to the third, mainly focusing on the conclusions from third, and both were released in consequent days, August 8th and August 9th. In his fifth paper, he calculated the received spectra for different temporal lightning stroke models. In the beginning of 1954, he showed that the curvature of the Earth could be neglected and calculated the propagation of properties of for two different sources, a horizontal and a vertical electrical dipole. In mid-1954, he published a two-part paper in which he elaborated on the radial Hertz potential of a horizontal source dipole in the spherical cavity and the corresponding transverse magnetic and electric waves. He also mentioned for the first time that the attenuation increases with frequency and therefore he expected only the lowest resonance frequencies to be measurable. And in 1957 was Schumann's last paper connected to the Earth ionosphere cavity oscillations. He emphasized that losses in the system have two consequences. The first is that the resonant frequencies change to lower values, and the second is that at higher resonant frequencies, the resonant effects are diminished. And after 1957, he worked with his doctoral student Herbert Koenig in this field. In addition to the Schumann resonances, there are also transverse resonances of the Earth ionosphere cavity, whose first specific calculations were performed in 1961 by Hermann Povlerin, one of Schumann's former colleagues at the Electrophysical Institute from 1942 1953, which is about 11 years. And about the term Schumann resonance, the first publication introducing the term Schumann resonances to the lowest resonant oscillations of the Earth-ionosphere cavity could be traced back to a paper by Charles Polk and Franklin Fitchen, both working at the Department of Electrical Engineering, University of Rhode Island in 1962. Two more influential reviews with the term Schumann resonances in 1965 by Janis Galeges and the other by R.K. Cole also increased the usage of the term Schumann resonance. For additional reading, I came across different articles and books for which I'll put up the links here to fulfill your curiosity. So, what might be the future of Schumann resonance? Well, our understanding of the Schumann resonance is still developing and how it influences our planet and life. So, there is a potential that it can be used as a diagnostic for planets with atmospheres. Perhaps with new research, we will discover the unique Schumann resonances of other planets which have their own ionosphere and experience atmospheric electrical discharges. And here's the bibliography. And with this, I'm ending my seminar. Thank you. Thank you for attending the seminar.